Welcome to our lesson on estimating a population standard deviation or variance. This is our third video in the series where we're trying to estimate a population measurement. In order to estimate standard deviations and variances, we have to use a chi-square probability distribution, which we haven't seen yet. So let's start by talking about what a chi-square distribution actually is. If we have a normally distributed population, and that population has a variance, we'll call it sigma squared. Let's assume that we just randomly select independent samples of size n from that population. So we keep sampling over and over again using good sampling techniques, right? We're making simple random samples of size, let's say 20, over and over. And for each one of those samples, we're going to compute the variance, and we'll call that now s squared. If we were to graph that distribution, that sampling distribution will have a chi-squared distribution. We've mentioned before that when we're doing these types of sample distribution estimates of the population, whether it's the proportion or the mean, that we had to make sure we were sampling from a normal distribution, or we had to make sure that our samples were greater than 30. Well, when we're dealing with the variance and thus the chi-square distribution, we no longer have that has to be greater than 30. It really just has to come from a normal distribution. So the requirement of a normal distribution is really critical for this test. If we sample from a distribution that isn't normal, then we get really big errors, and the results we get are really suspect. So you really want to make sure that you're verifying the population you're sampling from is actually normal before you apply a chi-square test to it. Here is the formula for our chi-square. Instead of, this is like when we were doing our z's and t's. Right, there was our z, and our t was relatively the same thing, except we didn't know the standard deviation or population. Now we're doing this for a chi-square, and just like our t distribution, we have degrees of freedom, and it's still n minus 1. Here's what a chi-square distribution looks like. Just like the t distribution, it changes shape based on its degrees of freedom. As the degrees of freedom get bigger, as you look at the graph on the left, as it goes from 10 to 20, you go from the blue line to the red line, and the distribution tends to look more and more normal. It becomes more and more symmetrical. The biggest difference between the chi-square distribution and both the z and the t distributions that we've looked at before is that the chi-square is always positive. And that kind of makes sense if you look at what's going on here. You're squaring a bunch of stuff, right? And when you square things, they're always positive. So you get a non-symmetrical skewed distribution. It's skewed to the right because it's always positive. It goes from 0 and above. But as the degrees of freedom go up, the tail on the left-hand side, right, gets bigger, and it becomes more and more symmetrical, closer to a normal shape, but it's still not centered at 0 like the normal curve is. These are just describing some of the properties that we looked at from the table, right? That they're 0 and above, degrees of freedom of n minus 1. And then if you want to look up critical values of chi-square in tables, they usually give you cumulative area located to the right of the critical, which is different from most z tables, which give you cumulative area located to the left. So that can be very confusing as well. How about an example? We take a simple random sample of 22 IQ scores. We construct a confidence interval for the population standard deviation by constructing these chi-square values, right? So the first thing we want to do is find the chi-square values that correspond to a 95% level of confidence. If we look them up in a table with degrees of freedom of 21, this is what we get. We can find those critical values using tables, as we see here, or if you want to use StatCrunch, you can find them that way. There is no way to get critical values out of your TI calculators, at least not the 83 and the 84. There might be a way in the Inspires or the 89s, the more fancier ones, but the 83 and 84 are going to be kind of useless for these, unfortunately. Luckily, however, StatCrunch does all of this. So if we want to find the critical values in StatCrunch, we go to Stat Calculators. Anytime you're trying to find critical values on a distribution, it's always going to be in the calculator menu. Chi-square brings up the chi-square curve, and you can do standard, less than or greater than something, or in between two values. We're just doing standard. First thing you got to do is give it its degrees of freedom, which for us was 21, right? Because our sample was 22. And down here, normally you would go, okay, what's the probability that something is less than 10 or something is less than 20? And it will give you the probability. But what you can do is just type in the probability and it will give you the critical value. So if we want our left-hand chi-square, since we want to be 95% confident, we want half of that below, so 0.025. Compute, there's our 10.28, 10.283, right? If we want to do the upper one, 975, gives us 35.479 if we round up. 35.479. Okay, so you don't have to use the tables if you don't want to. The tables are pretty easy. The bad thing about the tables is they don't have every degree of freedom in them. So once you start getting up into something above usually 30 or 40, then it goes up by every 10. So you can't get a perfectly accurate critical value, but you can always get a perfectly accurate one out of StatCrunch. Okay, so we now have our critical values. Now back to the second part of the question. Now that we've found those critical values, we then want to compute the 95%, right? 95% confidence interval for the population variance, given that the sample variance is 10.5 IQ points. In order to actually calculate our confidence interval, we need to now also know the sample variance. So that's the extra piece of information that we needed in order to do this second part. We can do that with our formulas. They're very simple formulas. If you remember, right, you would just type in 10.5 because variance is already the s squared. That equals variance. So you're not going to square 10.5. So if we were going to do this, right, we would have 22 minus 1, because that's our n, times 10.5 all over sigma squared equals chi squared, right? Well, we want to find this, and then we got this critical value. So it's kind of like a switcheroo. Solve in one for the other. So what we're really going to use is this formula. Do you see how we've solved for that standard deviation? But because it's not a symmetrical distribution, we no longer just have one version of it. We have both versions, the left side and the right side. And no, this is not a typo. It comes from the algebra of how you solve these things, that it just so happens that the chi-square right-hand side chi-square goes in the left side, and the left one goes in the right side. Fine, formulas are great, but wouldn't technology be a lot easier? Yeah, absolutely. So instead of this one, we go to Stat Variance Statistics, because we're running statistics on variances, one sample. Again, data would be if we had the raw data in a column. Summary is if we actually just have the summaries. So our sample variance was 10.5. Our sample size was 22. And we want a 95% confidence interval, asked to compute, and there it is. Lower of 6.215, upper of 21.443. There's our sample variance. technology is the way to go, guys. You don't want to have to use these formulas. If we were to use these formulas, for instance, the left-hand side formula would be 21, because that's n minus 1, times 10.5, because that's our sample standard deviation, and then we have to divide by the chi-square of the right-hand side. And if you remember the chi-square for the right-hand side, that was 35.479, and then the other side of the formula, 21 times 10.5 all over the left-hand chi-square, which was 10.283. And when you do that math, you get the exact same answer we just got out of technology, which is 6.215 roughly, right? And 21.443. So that's our 95% confidence interval for the variance of our population, right? If we wanted standard deviation, all we have to do, take square roots of everything, right? So take square roots of these two numbers, and then you have the confidence interval for your population standard deviation. Just like our other sample descriptors, the sample variance is the best point estimate of the population variance. The sample standard deviation, however, is biased, but it still is commonly used as the best point estimate because we really have no other good point estimate, but it is biased. We've talked about all these, you know what all these symbols mean. In order to do this, we still have to have that simple random sample, but here now, instead of worrying about sample sizes, we just have to have that the population has to be normally distributed. So that's a very strict requirement. Here's our work that we did before. Here's, a little cleaner if we want to do standard deviation. Constructing those confidence intervals, this will walk you through the steps of doing it by hand if you want to do it by hand. I don't know why you would. Technology is a lot easier. Another caution about interpretation, right? You can sometimes use confidence intervals to compare variations from two different data sets, but just because your two intervals overlap doesn't mean that those two sets might have the same variance. It's a very informal way of comparing, so don't read a lot into it. Here's another example with those IQ scores, where we're going to work the whole thing through. Our sample of 22, we have 14.3 is the standard, right? Standard deviation, not variance. Standard deviation of 14.3. We want to construct a 95% confidence interval estimate of the standard deviation. First thing we got to do, check and make sure our data is normal, or that it comes from a normal distribution. So we run a quick histogram, we look at that and go, it's normal-ish, right? It's normal enough. So now we can use technology to calculate all these things and come up with confidence intervals for the variance, and then square rooting them gives us confidence intervals for our standard deviation. What if we want to do these with technology? Well, let's get our numbers, right? Our n is 22, and we had a standard deviation of 14.3. So if we bring up StatCrunch, variance, one sample, summary, 22, but what do we put here? Right? We can't put the 14.3 because that's not what it is. We've got to figure out what the variance is. The 14.3 that they gave us, that was the standard deviation. So you got to make sure that you square that first, use a calculator or something, and then put in the variance. Confidence interval, compute, And now you've got those numbers, and you have to take the square root of those numbers. And if you take the square root of 121.03794, you get a little over 11. And then the square root of 417.61477 gives you 20.43. All right, there's the 121 and the 417 that we got. See? And then when you square root it, you get the answers that you're looking for. So really the biggest problem or mistake that you can make here is using standard deviations when you should be using variances, or forgetting to square things, or forgetting to square root things. You just got to be really careful to keep track of, are they giving you information in terms of a variance or a standard deviation, and are they asking for your answers to be in terms of a variance or a standard deviation. Determining sample sizes. The formulas and procedures for doing this are very complicated, so we won't even bother trying to do it with formulas as we did with proportions and means. There are tables, but like all tables, they are limited. StatCrunch, however, will do this for you. And I want to show you how to do this for all three. So we can do sample sizes for proportions, means, and variances and standard deviations all with StatCrunch. Stat. We'll start with variance, right? So we're dealing with variances. One sample, and then right here, sample size. This is doing hypothesis test power. That's a different measurement we can do later, but if you click on confidence interval width, this is now where it'll give you sample size. You'll notice that down here it's got your confidence level of 95. You need to tell it sample variance, how big you want your margin of error to be, and it will give you the sample size. So you just need to give it 3 out of the 4. Like if you give it sample size, confidence level, and variance, it'll tell you what your error will be. But if we want to go in the other direction, so we want a 95% confident. Let's say we go back to our IQ scores with a variance of 10.5. Sorry, variance, right? Not standard deviation. So the variance was like 121. And we want to be within, we want our interval to be within, let's say, 5 IQ points. Then we need a sample size of 42. It's just that simple. Okay, so that's how we can find sample sizes for our variance and standard deviation. Very simple, because if we were dealing with standard deviation, we just have to square things, right? The variance is just to square the standard deviation. If we wanted to find the sample size for proportions, go back to our lesson on proportions. Go to one sample, and you'll notice that it also has power sample size for those. So if you go to confidence interval width, you want to be 95% confident. This is the proportion of, right, that your p hat is. And let's say you want to be plus or minus 3%. You're doing polling, you want to be within 3%. Then that tells you how big you have to go out. You have to go out and get almost 4,300 people to be plus or minus 3%. Now, if we wanted to do it for the mean, so we're going to do t-statistics, because that's what we normally do with means. Sample size. Alpha, standard deviation, right? So this is hypothesis test, confidence levels. Alpha, standard deviation, how big you want it to be, and then it'll give you the sample size. So let's say we're standard deviation of 5.7, and we want to be within 10, plus or minus 10. Pretty small sample. But if we want to be plus or minus 2, bigger sample. Okay, that's for t's. What if we were doing means, right? But we knew the standard deviation of the population, and now we're dealing with z's, one sample, sample size, confidence interval. You're starting to understand, right? Same thing. Okay, so very easy to do sample sizes for all three: proportions, means, and variances if you use StatCrunch.